My name is Felipe Moretti Leila. I'm the program manager of the vertical solution MotionSolve. And today I'm going to talk about the validation of the MotionSolve tire soft soil model using the next generation NATO reference mobility model. To give you an overview, in this project, we use the NRMM or NATO reference mobility model data to create a digital representation of this military vehicle that you see in the screen using the MotionSolve vertical solution and the new Altair soft soil model. So physical experiment coming from the NRMM studies were then verified against the virtual models to assess the new soft soil solution, but also how the vertical solution that we have in MotionSolve can be used for such projects. With that, the agenda that I'll be covering today is a brief discussion about the NATO reference mobility model, then the next generation, the cooperative demonstration of technology, Altair soft soil solution, and then the project goal, which is the solution validated that we use to represent the vehicle and validate the soft soil model. And I conclude with a summary of what are the founds that we find doing this project. So what's the NATO reference mobility model? So the NRMM is a modeling tool containing equations for predicting the mobility of vehicles. It was developed by the Tank Automotive Research Development Engineering Center, TARDEC, in the US Army, and the Engineering Research and Development Center in the 60s and 70s. So it used vehicle, scenario, and terrain data as input, and output the prediction of the vehicle mobility, meaning basically the terrain trafficability and the maximum speed with this go-no-go threshold. In this picture, you see the workflow of the NATO reference mobility model. Actually, this is the NRMM2 that was issued in 1992, including the new equations. But here I give you an idea how the workflow works. They have basically the vehicle data, and then there is the scenario data and the terrain data. That's included to the main module. And as an output, there is the speed and the performance predictions. As you can imagine, this tool, this model has limitations. And basically, it is based on the empirical observation. It depends on in situ soil measurement. It's, of course, an old implementation developed in the 60s, 70s. And it considered only one-dimensional steady state for analyzing the powertrain. The turning and the lateral dynamics of the vehicle are not considering in this model. And because of that, the vehicle dynamics effect are mainly limited on the pitch plane. Okay. With these limitations, the exploratory team 148, followed by the research task group AVT 248, was created to develop the next generation NATO reference mobility model. So this research task group ATV 248 was initiated in 2016, and they analyzed 7 main areas. The first one was the GIS, terrain and mobility mapping. Then they follow with the simple and complex aeromechanics. There was the intelligent vehicle area, uncertainty treatment on the soil data. Then the verification validation of the vehicle and the performance of the solution on the soft soil terrain and rigid terrain. Then there was the data gaps and the operational readiness. So all these results was then exposed in this cooperative demonstration of technology, the CDT 308 event. So basically, they spent more or less 2 years studying these areas, and everything was presented in this conference, CDT 308. So what is the CDT, the Cooperative Demonstration of Technology 308? So the CDT was organized basically, as I mentioned, to demonstrate these 7 technologies and also to conduct the verification validation exercise. Okay, and for that, they use this full efficient demonstration alpha, which is we call Fed Alpha, that was selected as a test vehicle. So they invited commercial software to model and simulate this vehicle and studies the effect of the vehicle mobility on soft soil terrains and on rigid terrains, and to give you a clear view of what was developed actually in the operative demonstration of technology, I have this YouTube video that I want to play for around 1 minute so that you can understand better what is the NATO, what is the CDT, and what's the goal of the project that they had. Okay, just 1 second. I'm going to play this now.
You want to follow the undulations in the terrain, and you just want to be able to pop up the turret of a tracked vehicle to engage the enemy, then you want to back down and maneuver around it. If you don't have the mobility of that vehicle to do that, you're more than likely going to have to take a path that exposes yourself, highlights your vehicle against the backdrop, which makes you a target.
If we can quickly get out of an ambush situation, that saves lives. Getting stuck and not being able to predict mobility ends the mission, but also makes the soldiers very vulnerable to enemy fire, makes them a sitting duck, a target.
Mobility equates to survivability. Our combat formations have to go across cross-country terrain, secondary roads, primary roads, and so we need to be able to move throughout the battle space, and if we can't move to where we need to, then it puts us at a disadvantage against our enemy because they can predict where we're going to be at.
All right, I hope this gives you a clear idea what was the CDT. And now let me talk about the Altair soft soil solution. So Altair provides a way to simulate the dynamic behavior of tire and track system on compressible terrains, right? That includes clay, dry sand, and regolith simulant, for example. If you haven't done so, there was a GTA that happened last Tuesday that explains in detail what is the tire soft soil solution inside MotionSolve. But basically, we implement in MotionSolve a new tire and road contact model that includes basically the Beck-Wong and Janot's formulations for soft soil terrains. It is a fast and memory efficient method to calculate this, and we can include any type of terrain, complex geometries, external files, and scanned roads. Now, this soft soil road is included inside MotionView through this and MotionSolve through this soft soil road data. Okay, these road data then can be used in the tire models that we have, but also in the track systems and simulating the events. For those that does not have this information about the soil, we are also providing the installation a package that contains several types of soil data that can be used. And if you want to visualize and studies the effect of the vehicle on the terrain regarding the plastic sinkage, shear, and stress strain, we can also load these soft soil file into MotionView road tools and visualize the deformation of the soil. Now let's talk about the project goal. What's the idea? We saw that we have this data provided by the NATO, right? So the next generation NATO reference mobility model, they present everything on the CDT, and this CDT consists of this test. They provide the test data of this vehicle, perform different maneuvers, and we also have the MotionSolve soft soil validation model. So the idea was to use the NATO reference mobility model data into MotionSolve to create a vehicle, digital twin of this Fed Alpha vehicle, and validate the solution that we have in MotionSolve. To do so, we mainly approached 3 steps, right? The first step was the representation of the Fed Alpha in MotionView, including all the detailed information available through the CDT. Then we progress with the second step, which is the simulation on rigid terrain. This second step was mainly to validate the first, validate if the modeling representation of the Fed Alpha was done in the proper manner. And finally, in the third step, we perform the validation of the soft soil model. We start with the first one. As I mentioned, the idea is to create a digital representation, a digital twin of the original vehicle. And to do so, we use the vertical solution inside MotionSolve. We start then with the CAD data that they provided. And with the CAD data, we extract the hard points location, the mass Nash, and the geometry of the vehicle. Then, using the vehicle library inside Motion View, we build the suspension models, the steering system, the drive line. Okay, so we took the data, the available data for the Fed Alpha vehicle, and we including into the components that we have in the component library in Motion View, mainly the tire, the air spring, the shock absorber, the bump stop, and the bushing. This was then used to complete the representation of the visual system, like the suspension, the steering system. Then, to analyze if these systems were well represented, we validated using test rigs. So mainly we take the suspension system, the tire system, and perform test rigs to understand if the behavior of these components was identical with what was provided by the test data. After define the suspension, the models, we need to have a powertrain in this vehicle. Now, this vehicle contains a different powertrain. It uses automatic transmission powertrain with some regenerative electrical module inside. And we didn't have this inside the vehicle library. So we developed a completely new powertrain model, mainly including the torque converter, the gear, the engine, and the shift logic. This development was done in Twin Activate. And it was also, okay, after this project, we also include this powertrain representation inside Motion View, and it's now available in Motion View 2023 as part of the vehicle library. Now, with all this done, okay, powertrain, validation of the suspension, representation of the model, we start building the pieces together, starting with the front suspension, rear suspension, drive line, then the powertrain, to then build the full vehicle model. And once this was done, we moved to the next phase, which was the validation of this vehicle on the ridge terrain, just to make sure everything was set properly. So the CTT had performed 10 different tests, and the idea was to replicate precisely what they have done in the test using the MotionSolve solution. Okay. Now I'm going to go one by one to explain what are the tests and also show the result and discuss a little bit about what we got from them. So we start with the straight line acceleration. The idea of this event was to validate the powertrain performance. Here we have the vehicle starting from the rest and then reaching a maximum acceleration. Here you see the plot of the longitudinal velocity, longitudinal acceleration, engine speed, engine torque, and transmission output torque. The black lines are the MotionSolve simulation, and the blue line are the test data. The next event was the straight line braking. The idea here was to verify the suspension response and the brake performance while doing so. So the vehicle starts at a speed of 40 miles per hour, reaching the full stop. Here you see the longitudinal velocity, longitudinal acceleration, the vehicle pitch, and the pitch rate. You may see that the vehicle pitch is a bit off regarding the test and simulation. That's an issue that is there on the measurement signal. It will use GPS to measure the pitch, which is not very accurate. And that's why you use the pitch rate to provide a better understanding of the pitch effect. The next event was the wall-to-wall turn. The idea of this event was to validate the steering geometry of the system. Okay, basically the vehicle rotates the steering wheel and perform a 360 degrees round. And you can see in the plot the test and simulation for both clockwise and counterclockwise directions. The next event then was the steady state cornering event that was used to mainly verify the handling characteristic of the vehicle. Here you see the steering wheel versus lateral acceleration and lateral acceleration versus vehicle speed for both clockwise and counterclockwise directions. Then we have the double lane change event. The double lane change was used to verify the stability of the vehicle during the obstacle avoidance. And there are actually two events inside this double lane change. The first one was a calibration. So it was an open loop event where the input of the steering was predefined and the vehicle has to follow the double lane change. And that's what you see in these two plots here, the vehicle roll and the lateral acceleration at 30 miles per hour. Now, the second event was again a DLC, but performing a maximum speed calculation. So basically, we run a range of speed, and we keep measuring the boundaries of the vehicle regarding the event. So here, the black lines correspond the event, and the idea is that the vehicle should not go beyond these lines. And to do that, we managed to reach a maximum speed of 40 miles per hour. And here you see the animation of the vehicle trying to run at maximum speed on this circuit. Now, the other event that we performed was the side slope obstacle avoidance. The idea of this event was to verify the stability of the vehicle on a low friction side slope. This side slope is a 30 degrees slope. And as you can see, it is a soft soil, right? But because it was not easy to quantify and to measure the soft soil properties, the CDT suggests that it was suggested that we represent these as rigid ground with a coefficient of friction of 0.47. This road is basically a packed gravel and should be considered non-deformed in this case. Now, the event is similar to the double lane change. We have an obstacle, let's say, offset by 3 meters, and the vehicle has to go with a low speed around this obstacle. Yeah, and here you see the longitudinal velocity, lateral velocity, vehicle roll, and your vehicle yaw angle against time. Now, another event that was performed was the 6% grade climbing. Here also there was two sets of analysis to be done. The first one was the ability to climb the 6% grade. So the vehicle started from the bottom and then went to the climb and reached the top. The second event though was a test on the parking brake. Basically, the vehicle went to the climb, stopped there in the test. They switch off, apply the parking brake, switch off the engine for 2 minutes, then restart the engine and start climbing. In the simulation, you start the vehicle already in the right position, just initiate it to see if the vehicle could manage, could perform the analysis or not. Then we had the half round event. The half round was executed to verify the ride quality of the vehicle. This was done by assessing the vertical acceleration at the driver's seat. So different speeds were performed in the 4, 8, 10, and 12 inches half rounds. And the ride quality was verified by the 2.5 G's acceleration at the driver's seat. So you see here the slow motion of this event. On the plot, what is basically showing for each speed, okay, what are the acceleration that was achieved for a specific half round. And the lower plot here, you see the acceleration at the driver's seat, okay. The other events were performed to validate the negotiability of the vehicle. The first one was the V-ditch obstacle. The idea of these events is to validate if the vehicle body would hit the road. So the V-ditch managed to negotiate without it. Then there was the vertical steps, which are basically these steps on the road, and the vehicle has to cross it. It was performed 3 main tests with 12 inches, 18 inches, and 24. The 12 inches, you see that the vehicle performed well, I mean, passed through the obstacle without hitting the body. With the 18 inches though, it hit the front when it starts, and then at the end also hits the body. And the last ridge event was done with the RMS, or the root mean square courses. So it was executed to validate driver comfort. So this was done by assessing the maximum speed that would give an absorbed power at the driver's seat of 60 watts. So it was run in the asymmetric course, but also the symmetric courses. So basically 5 symmetric RMS course was executed and 2 asymmetric courses. Here in the plot, you see the RMS height and the vehicle speed, and basically telling that, for example, let me use this. For a RMS height of 3 inches, the maximum speed that's allowed to reach the 6 watt was around 10 miles per hour. Now, this concludes the rigid events, and now we move to the third step, which is the validation of the tire soft soil model. Okay, it starts by modeling the Altair soft soil road using the vivometer and the cone penetrometer data. So basically, just to briefly explain, the vivometer performed two tests that you see here. The pressure sinkage using this plate that mainly push the soil down, and then the soil shear stress that consists of this disc here that has some grouses, so it's pushing the soil and rotated. Now, the outcome of this vivometer is showing this table here, which are basically the Beckman coefficients. And we could use these directly in the Altair soft soil model as we use the same Beckman formulation, right? So basically, the first step of this characterization was to take these coefficients that were provided by the CDT event and include into the soft soil road model. The soft soil model was then included in the tire model and performed the simulation. And to verify the model, two tests were performed. The first was the drawbar pull that measured the towing capacity of the vehicle. And for this drawbar pull event, three different soils was used, mainly the fine grain sand, dry and wet, and the coarse grain sand, dry. And for the variable grade sand slope, it basically performs the vehicle in a variable slope from 0 to 30% gradient. And in this case, it will use the coarse grain soil dry. Now, to show you now the results, we have for the drawbar pull, right, the vehicle on the soft soil. There is this towing vehicle behind it that was applying brakes to perform, a drawbar pull force on the vehicle itself. The vehicle gets stuck after some time. And here you see the plots, right? So the plot represents mainly the drawbar as a percentage of the gross vehicle weight, or GVW, in function of the slip. As the force applied behind the vehicle increase, the slip also increase and the vehicle gets stuck. Now you see that in the test there was this chunk of test files here. These are because it was used for different value of force. In the MotionSolve's simulation, we could then do it gradually, so we can capture all the value of forces. And here you see the correlation for the first fine grain sand dry, and then here is the second with fine grain sand wet. And then you verify this one, which is the coarse grain sand. And it's a bit far away, and I'll explain this a little bit later. Okay, then we have the second event, which is the vehicle performing a slope climbing from 0 to 30%. Here, the idea is that the vehicle will start climbing, but because the soft soil, it gets sinked and then stop. So you see on the plot the longitudinal slip versus time here. This was done for the rear left tire, but basically they should be very close, all the tires, because we have a locking differential applied in all the wheels. Then we have here the slip versus slope and the slip pitch. And here the measurement on the pitch also shows this difference here. Okay, as a summary, and what we found with these results, we have mainly that the fed alpha vehicle was fully characterized using Altair multi-body solution. We managed to represent everything. There was not even a single modeling that was not possible to include. We captured all the test data and was able to represent everything in MotionView and MotionSolve. The simulation performance on rigid terrain closely correlates with the test measurement, as you could see in the plots. But we saw, however, that for the vertical dynamic studies, for, let's say, the half round and the RMS events, although good, the results were a bit influenced by the simplified tire model. And that's known to us. And it's known because we didn't want to use here a 3D part tire solution to capture the vertical dynamics, which is needed in this case of this analysis that consists of CD tire or F tire or MF sweep, as the main goal of the project was validate the soft soil. So we kept with the MF tire that we have, this free of charge. And the intention of this work is also to share with people, and we don't want them to have this extra license to run the model. Now, talking about the soft soil, the Altair tire soft soil predict the vehicle behavior on the former terrains, but due to complexity of the tire mechanism measurement and the representation of the large grain particles that you saw with the coarse grain soil. The results for the fine grain was much better. And this is pretty much aligned with the theory of the soft soil, what Beck and Wong equations provide, right? So whenever you have this coarse grain, the physics of the thermomechanics is a bit complex, and it would be better to be represented using EDEN, for example, right? To represent with a discrete element method. But for soil data such as fine grain sand or mud, these would be very well represented. So consider then this semi-empirical contact model and the test result also variability. This new tire soft soil method presents a very efficient method to assess the vehicle behavior on deformed terrains. Also because the simulation runs very fast compared to other solutions like discrete element method. And the outcome of it is very close to what is required. So if the user needs to perform design studies or validation of the vehicle, performance of the vehicle on these in a quick manner, this soft soil model is suitable for these applications. Now, this ends my presentation, but I want to mention two more topics. What is next, right? So what we have available for these, we show you the results, and the idea that we want is to make these available to you, right? So with that, we are providing a package, a zip file that contains the model, the set already for the rigid and soft soil events. There is a README file on it that explains precisely what has to be done to execute all the models and verify the results. And because this is a very extensive work, right? So we run several events, analyze several parts, model the full vehicle from the CAD to the end. So I couldn't cover everything in this presentation. So what we are providing is a PDF document of 70 pages that explains all the steps that you use to either create the model, also a brief introduction of what is the NATO, what they are doing there, and also how we simulate all the results, right? I show a few results here, but there are many more results, and basically a few conclusions that we got on the tire model, on the soft soil is all showing there. All right, that reached the end of this presentation. I thank you very much for the attention.